All right, folks. Today I'm going to talk about the problem with using R squared. R squared is probably the most famous regression metric out there, and yeah, I wanna discuss with you um, why actually the information provided by R squared is very limited. Okay, R squared is also known as the coefficient of determination. Okay. So yeah, that's my goal. Show you, why R squared actually give us limited information. Then discuss an alternative metric to R squared. And then finally, I will point out, let's say, a more appropriate use of R squared. Okay. All right, perfect. So I'm gonna do all my analysis in this notebook, and I will share a link to this notebook in the video description. Okay. The data set I want to use is the diamonds data set, which you can read here. It's part of the ggplot2 package, and at the same time, the ggplot2 package is part of the tidyverse package. So when you install the tidyverse package, you get access to the ggplot2 package and to a bunch of data sets, and one of them is the diamonds data set. Okay, so if you need to install the tidyverse package, you are going to comment that line of code out, okay? And then you're going to install the tidyverse. I don't have to do it because I already did. But yeah, if you need to do it, just remove the comment right here and run that code cell, okay? All right, that's to install the package. To load it, we use the library function and then the name of the package. And let's load the tidyverse, okay? And it's loaded. And as I told you, once you load the tidyverse, you have access to the diamonds data frame. Okay, let's take a look at the diamonds data frame. It's a data frame with data about 53,940 diamonds. And then for each diamond, we have, they collected a lot of data, like number of carats, cut kind of type of cut, the color, so on and so forth, the price of the diamond, okay? Like a bunch of information for each diamond, all right? And the task that I want to do is this. I want to obtain a linear regression equation to predict the price of the diamond based on the carat amount, okay? And I want to evaluate the quality of the equation. Now, to evaluate the quality of the equation, I will use R squared, and then I will discuss the limitations of R squared, okay? All right, guys, so let's run this regression between price and carat. And to run this regression, I'm just going to use the old and well-known LM function. Um, and for LM, we need to specify what the target is, which is price, and then tilde. After tilde, we specify the predictor or predictors in your equation. In this case, it's only one carat. Then you need to specify the data frame where these columns should be located, and that data frame is diamonds. And yeah, that's it. But it's usually customary to store the regression results in a variable. So let me go ahead and call this variable something like uh, let me call it regression price. Okay, regression underscore price. Okay. All right. So that variable stores the regression results. All right. Now, what you do is you invoke summary, the summary function on that variable, and you will be able to see the regression results. So regression price, and then there you have the regression results. Okay. Now, guys, remember to analyze the results of a regression analysis, we need to do two steps, right? First, we need to evaluate the statistical significance, and then we need to evaluate the practical significance. And the practical significance is actually what allows us to evaluate the quality of the equation. So the quality of the equation is given by its practical significance, okay? All right, two steps, statistical significance, practical significance. In this video, I'm going to skip the statistical significance. I want to, kind of make the video shorter and focus on the R square issue. So, but yeah, you should first do that, evaluate statistical significance. And I will tell you that this equation is actually statistical significant, okay? And there are a bunch of videos, YouTube videos, uh, web posts about how to evaluate statistical significance in regression, okay? But anyway, so statistical significance is a given. We have a statistical significance. Let's focus on practical significance. To evaluate practical significance, the practical significance of a regression equation, most analysts will focus on R squared, right? And a few things about R squared. Remember that R squared is a number between 0 and 1. The closer to 1, the better the equation is. And actually, R squared tell us what percentage of the total variability, remember that term, total variability, what percentage of the total variability is removed by the regression equation. I'm going to discuss that definition a little bit more later, okay, with more details later, okay? But yeah, so what percentage of the total variability is removed by the equation? Okay, in this problem, R squared is 0.8493. So R shows R squared under that name, multiple R squared. That's R squared. So 0.8493, we usually convert that into a percentage. So it would be 40, I'm sorry, 84.93%, right? So 84.93%, it's almost 85. So we can say that the R squared for this regression equation is 85%. Now that's usually considered high R squared. Okay, an R squared of 85%, it's considered by most analysts as high because they will say something like this equation allows us to eliminate 85% of the total variability, so this is a good equation. Okay, and that's all right, but guess what? If we use a different evaluation metric instead of R squared, we get a different conclusion, guys. And that different evaluation metric I want to focus on is the residual standard error, which is also provided by the R output. Residual standard error, or RSE. Okay, residual standard error, or RSE. You can see there that the RSE is 1549. And to interpret the RSE, we need to consider a few things. First, RSE is in the same units as the target. What is the target variable in this case? Price, right? Diamond price. So it's in dollars. So actually RSE is $1,549. Okay. And if we want to interpret that $1,549, we would say would say like roughly, because it's actually an approximation, roughly the price predicted by the equation deviates. That's the key word, deviates. So the prediction given by the equation deviates from the actual price by that amount, by $1,549. And if you want to know if that deviation is small or large, okay, where like small means good, small deviation is good, and large deviation is bad. If you want to know if that deviation is bad, you need to actually do an extra step, because the problem is RSE is scale dependent. So to be able to judge how small or large RSE is, we need to make it relative. Okay, and the way we do that is we make RSE relative by comparing it to the mean of the target. So we compare RSE to the mean, in this case, the mean price. Okay. And that comparison is actually what the coefficient of variation does. So in your stat one class, you learn about the coefficient of variation, which is simply the division between the standard deviation and the sample mean. And actually, RSE is actually the standard deviation around the regression equation. So in short, to make the RSE relative, we can compute a coefficient of variation using RSE. So by dividing RSE by the mean of price. Okay, and again, that's what the coefficient of variation does. It's just what percentage of the mean does the standard deviation represent? Okay, and again, RSE is the standard deviation around the regression equation. Okay, and once we have the coefficient of variation, guys, then we are able to interpret how small or large RSE is. Okay, but let's compute the coefficient of variation first, and then we can interpret it. To compute the coefficient of variation, we just divide, as I told you, divide the coefficient of variation, which is the standard deviation around the regression equation, by the mean of the target. In this case, the target is price, so by the mean price. Oh, sorry, price. And we can leave it like that as a proportion. We prefer to represent it as a percentage. Okay, that's the standard thing to do. So in this case, The coefficient of variation is 39.38%. Okay. And this is the thing, guys, for the coefficient of variation, there are actually well-known benchmarks, if you will. Okay. So for the coefficient of variation, the idea is we want a coefficient of variation to be less than 20% and ideally less than 10%. So in other words, we want the standard deviation to be no more than 20% of the mean. And ideally, we want the standard deviation to be less than 10% of the mean. Okay. So ideally less than 10%, uh, but definitely no more than 20%. Well, this is 40%, guys. Okay. The coefficient of variation is 40%, like it's way above the 20% threshold. Okay. So what that tells me is that because the coefficient of variation is so large, then the RSE is also large. That's the way you interpret RSE. Large coefficient of variation, way above the threshold of 20%, then RSE is large. Okay. And yeah, so if RSE is large, that means that the prediction error of our equation is too large, meaning like the equation is not a good one. It's not a good equation, okay? Well, here we have a kind of contradiction, right? Because we have two metrics, R squared and RSE, painting a different picture about the quality of our equation. R squared tells us that the equation is good because R squared is 85%, is large, and RSE is telling us that the equation is not good because the coefficient of variation for that RSE it's 40%. So what's going on? How do we explain that disagreement? Well, I will explain that disagreement by doing a scatter plot. And in that scatter plot, I will actually, the scatter plot will actually allow you to see what really R squared is telling us, what information R squared is giving us. And it will also help you see its limitations, okay, the limitations of R squared. And I will also be able to show you with that scatter plot the um, the real meaning of RSE. Now, the scatter plot I'm going to do is just a scatter plot of the target price versus the predictor versus Carrot. Okay, and in that scatter plot, I will display two lines: the regression line and a horizontal line representing the average price. So two lines you'll see. So the regression line and then the horizontal a horizontal line representing the average price. Okay. All right, let's go ahead and do that scatter plot. Now, to do the scatter plot, I'm going to use standard base R functions, okay? We could use ggplot2 functions, but I'm gonna just use base functions, okay? Like built-in functions in R. Okay, so let's do a plot, as I told you, to plot the, first we specify the x-axis of the predictor carat, diamonds, carat, and diamonds price, okay? Look, good price and carat, good. And as I told you, I want to actually show two lines. I want to show one line. To show that line, I'm going to use that function AB line, a line representing the regression equation. And to that, I'm just going to use the regression formula that I used over here. I'm going to say, I'm going to tell R, hey, I want to use that function to plot that line. And I guess I'm going to use a red color for that line. Okay. Sorry. Red color for that line. And let's see, let's take a look. That is great. I probably want to make the line a little bit wider. So line width 2. Yeah, yeah, much better. And I'm going to also, as I told you, do another line, which is just a horizontal line. It's a horizontal line representing the mean of the target, which is the mean price, right? The mean price. So from diamonds, compute the mean. Sorry about that. Trying to use the auto completion diamonds, use price. There you go. And I'm gonna use the same color. Maybe you want to use a different color for the horizontal one, but I'm just gonna stick to red and the same width. Okay. Yep. All right. That should do it. All right, guys. So let's try to understand what R square is telling us from this chart. Well, here we have the horizontal line, right? The horizontal line is just the mean price, the average price, right? Well, look at the variability, like how far away are the data points from the horizontal line, right? The variability around the horizontal line is just like how far away are the data points around the horizontal line. Like most of them are really far away from the horizontal line, right? The data points are really like on average very far away from from the horizontal line. In other words, the horizontal line doesn't capture the relationship that we are observing in that chart because that horizontal line for the starters, it's unable to capture the upward trend. Like the data points follow an upward trend, and obviously the horizontal line doesn't capture that. So on average, the data points are really, really far away from that horizontal line. So the horizontal line doesn't capture the observed trend very well. Guys, that variability, like the variability of the data points around the horizontal line is what I mentioned earlier, the total variability. So the total variability is the variability of the data points around the mean of the target. Okay, that's the total variability. So total variability, the variability uh, of the data points around the mean around the horizontal line. And in this case, that variability is very large, as we just discussed. Okay, perfect. Let's take a look at the regression line. Well, the regression line has a positive slope, and it somewhat captures the upward trend, right? Because you have a positive slope, so it captures the upward trend. So obviously, you can see that on average, okay, on average, the data points are kind of closer to the regression line than to the horizontal line. Okay, so like the level of variability, like let's not talk about variability, like how far away are the data points from the regression line? If you compare that to how far away are the data points with respect to the horizontal line, you will see that the data points are farther away from the horizontal line. Okay, so again, the data points are kind of closer to the regression line compared to the horizontal line. Okay. And guys, that's what R square is telling us. Okay. R square is just a measure of how much better is the regression equation with respect to the mean. All right. That's what R squared tells us. Like, how much better is using the regression equation instead of the mean for making predictions of the target variable? Like, if you want to make predictions of the target variable, how much better is using the regression equation instead of the mean? Okay. And the fact that R squared is high, like in this case, 85%, doesn't mean that the regression equation is good. No, it tells us that the regression equation is better than the mean. Okay. So high R squared, that means the regression equation does a much better job than the mean for predicting the target. But it doesn't mean the regression equation is good. Like an analogy, like in many situations, you can claim, for example, like, oh, like B is better than A, but that statement doesn't mean that B is good. B is better than A, that's fine, that's okay, but then that doesn't mean B is good. Same thing. So the regression equation is better than the horizontal line, than the mean. Okay, that's what R squared is telling us, but that doesn't mean the equation is good. And that's why when we look at RSE is telling us that the equation is actually not good because RSE measures directly the level of variability around the regression line. Remember what I said earlier, RSE, it's a measure of the standard deviation of the data points around the regression line. RSE is a measure of the standard deviation of the regression point, I'm sorry, of the data points, okay? RSE is a measure of the standard deviation of the data points around the regression line. So RSE directly targets the variability around the regression line, and it tells us whether that variability is large or small. And in this case, we concluded that the variability around the regression line based on RSE is large. Remember, when we computed coefficient of variation, it was 40%. That's too high, okay? All right, guys. So to conclude, let's kind of conclude with three ideas. The information that R squared gave us is limited. Okay, R squared only tell us how much better the equation is with respect to the mean, but that doesn't mean the equation is good. Okay, RSE is a much better metric about the quality of the equation. Like you can actually use RSE to conclude whether the regression equation is good or not. And the way you do that is, you from RSE you compute the coefficient of variation, and if the coefficient of variation is less than 20%, that's acceptable. Ideally less than 10%. But anything, if the coefficient of variation is above 20%, that means the RSE is large, which means that the regression equation is not good. And finally, remember I said at the beginning, I was going to mention like like a kind of more appropriate way of using R squared. Well, guess what? You can use R squared for comparison purposes. What do I mean by that? Like if you want to compare like a few equations, you have two equations or three equations or four equations, and you want to see which one of those four equations is best, R squared can help you with that. The higher the R squared, the better the equation is. Okay. So R squared is a perfect metric for comparison purposes. Okay. Um, like to compare across equations. But if like using R squared to evaluate a single equation in isolation, that's a problem. Using R squared to evaluate a single equation in isolation, it might be misleading because you can get a large R squared, but that doesn't mean the equation is good. Okay. Like in this case, we noticed that because RSE was too large. Okay. All right, guys. So I hope you understood the limitations with R squared. And thank you for watching. I will see you in another video.